Streaming.
And I'll start recording when the show starts, or I can do it right now.
You can do it right now, but it's like however you feel comfortable, when you feel comfortable.
Well, I have this SSD. I have 5.5 hours.
Okay. See, right now it's like this is going live. So when I go here and I need to change when it starts, just transition, and then it just sends that over. Also, we're gonna add. Did you download the images also there on the spreadsheet? First, we have 2 images. I think it was there.
Those two?
Yeah, those 2. So this was the first session, and after lunch you're gonna this is just gonna put on for when it starts. For a moment visible, and that's it. Just throw that into there. And number 1 is for the first one, and this number 2 is for the after lunch one.
So this thing, just drop it off?
Yeah, add it. I don't know. You can drop. I did work with drag and drop also. No. Existing one. That's something that exists already. Create a new.
Yeah, I'm not super familiar.
Just name it scene 1 or like a loitered 1 or whatever. Okay, now just okay. Now browse and grab the 3, 1. So this will be the first session. So when it starts, have that on for like a minute maybe, and then take it off. So this will be just like.
Okay.
You can also right click on this show transitions with like fade and also outgoing. High transition, fade. Now it should, when you press that, it fades in and it's out. And so you can put the second one. Yeah, that's gonna be going for the lunch time. After lunch, like the session. Okay, I need to check my room.
Thank you. Слышишь, там, оказывается, были все эти заставки, таблички, паузы на брейке, все что у них было. Да, короче, открывай свою комнату, в табличке этот...
Hey everyone, thank you for attending and bearing with us as we figure out these technical issues, and hopefully it'll just be another like 5 or 10 minutes.
Ну вот в табличке, которая AGI-24 Streaming Timeline, там открывай свою комнату, и там у тебя 3 файла: Stream Lower Third, Stream Video, 5 файлов нужно скачать, ну, по крайней мере, у меня. И там, да, окей. Давай.
Okay, yes, that is possible. We're grabbing another one. It's working partially, so the last word on change.
Короче, хотела сделать, да? Ладно, давай.
One step at a time. Yeah. Don't overcomplicate it if we don't have to. Hoping it's just that would be a simple solution. And then the last question is like outside. Will the other yeah. Actually, what are yes, that's what I was describing. Oh, this case right here. Oh, I feel like this guy in. As you can see, yeah. Instead where it's like in the shadow of all the huge data centers,
Yeah.
We were talking with Dimitri, and we're having him join the Zoom room so that when we have virtual presenters, you can stream the Zoom room out to YouTube. Is that something that you can do from here?
Not super familiar with that.
Okay. Can I have you join the Zoom room, give you the information? Oh, you've got this. Great. Oh.
Yeah, I have this thing.
Do you have the Zoom links here? You don't. This is the stream keys.
That's all they gave me.
Okay. Let me give you the, and then maybe you and Dimitri can you guys are in contact?
Yeah.
Coordinate on how to switch between.
Yeah, I don't see any information in here.
I've got Rainer over there if you want to communicate with him. He's whatever it is.
This is the Zoom link?
He needs to join the Zoom room so that he can stream the Zoom room when there's virtual presenters to YouTube. Okay.
I think this is it.
Yeah. You do have it. Great. Now I think
I'm not sure if it will work here. I've never done this thing with the
I
Zoom.
think you've got all live presenters for the morning session. So as long you should be in here just so that
Yeah.
we've got this part, and maybe you can talk with Dimitri about what he's doing down in the other room, or Rainer. He's doing it. He'll be doing it.
Okay. Yeah, just in case I have the meeting right here.
Yeah. Go ahead and join. You can be in the room, and that way you can.
Yeah, I need to set it up first. Okay. I mean, if you say I'm not gonna have any Zoom speakers.
I don't think you've got any virtuals. Let's see. Rachel's not here, but Peter's here. David will be here. Chris is here. So yeah, these are all.
So yeah, I'll set up Zoom during the lunch break then.
That sounds perfect.
Okay.
And I don't know if these are all live, but I will find out for you. Okay?
Thank you very much.
Yeah,
Appreciate it.
absolutely. Thank you for being flexible. Hey, Peter.
Sure.
Renato, I'm Haley.
I thought it was one of those read, sign your life away, give me your firstborn child.
If everybody was my firstborn, I need more firstborns, octuplets at least.
Okay, so that's the only thing. That's the only thing. Great. The other one is the system just needs to be. It needs to be turned off or turned back on. You know the oldest chicken store. Yeah.
Oh,
Yeah. It's actually in the ceiling. Every once in a while on a Sunday. Always be right after.
We can start?
Need anything?
Not right now. We can start?
I think they're almost there. Just wait for them to signal.
Uh-huh.
That will be for your laptop.
Yes, please.
Yeah, we need to see if Haley can hear us when we're talking this.
I can hear you guys. Sounds really good.
Thank you.
We can hear you. Yeah, we can hear you, Haley.
Fantastic, and the camera looks fine too.
Okay, thank you. Okay, so we only have a couple of people online, but for everyone in the room, thank you for coming. We'll get started. Thank you so much for your patience, 35 minutes. So my name's Chris. I'm the CEO of Mind Children Robotics. And I guess I'm maybe taking over to introduce everything. Unfortunately, Rachel was unable to make it. David Hanson's flight got delayed this morning. So we're trying to get everyone logged in so that we can still have everyone involved in the conversation this morning. A little background about myself, and then I'll pass it off to the rest of the panel up here. My background is in product design, and I started working with SingularityNET on the Mind Children Robotics project about a year ago, and we're developing a new humanoid robot that it's about 3.5 feet tall and completely geared toward human interaction. So we're looking at implementations in education, hospitality, healthcare, and still very early on in the project, but very relevant for us to be talking about episodic memory in this discussion. So I'll maybe pass off to Sergey to introduce himself, but with one additional last comment that we're in this, Sergey and I are in this very early on beginning phase with our project where we're not at a point where we can participate like Hanson Robotics in some of this testing, but it's very applicable and interesting for us because we're still deciding how to do these things in our project. So that's kind of the mindset and the view that we'll have on it this morning. So, sorry.
Yes, so Chris, children, and I'm like kind of responsible for.
Can't really hear you back here.
Yes, sorry. Can you hear?
One, two, barely.
Okay.
You want to come to
Okay, I will speak louder. So I am responsible for AI in Mind Children, and yeah, my background is in AI and before in statistics, but it's not relevant. Yes. So and we will be the users, like consumers of what Simuli will offer us, probably, if they will convince us to use it. Yeah. So next Simuli.
Hi everyone, it's a pleasure for me to be here. My name is Renato, you can call me Ram. I've been involved with Simuli since last AGI conference, AGI-24 in Sweden, which is where I met those beautiful people. And today we are here, we are presenting our workshop on memory-enabled motivational agents. So I think that, I don't know, Peter, if you wanna jump in and then we can actually start with our slides, and after the slides there will be an actual demo that you can also play with. We will be sharing the material because it is all like open source feature at this stage. So thank you again for having me.
Hi, my name is Peter Suter. I'm a PhD student at University of Maryland, and I also work with Simuli, with Renato, on various things, usually involving hyperdimensional computing, which is what my PhD is also in. And hopefully, we'll show you how maybe hyperdimensional computing can help with some of this idea of episodic memory and this idea of a soul engram, as we're going to show in our presentation. And yeah, that's pretty much it.
Maybe after. Yeah.
Before I start, I imagine that most of you will be familiar with large language model, but I don't know how many of you are familiar with the RAG framework. So is there anyone in the public, don't be shy, that is not familiar at all with retrieval augmented generation? Okay. So I will start with a very brief recap of what RAG is, and essentially retrieval augmented generation is an approach that involves the generation part using large language model and retrieval-based methods. So the idea here is to improve the factual accuracy of the responses generated by a large language model, reduce the number of hallucinations, and improve the contextual understanding of the queries that are being presented to the LLMs. So the original idea was quite simple. It was introduced in 2020 in a paper by people at Meta. Nowadays, RAG has become like its own full framework, and it's mainly divided into 3 areas of research. That is, like, of course, fine-tuning, but then there is also inference and pre-training. So the original approach had as a core idea, again, to enhance the LLM capabilities by providing it with a knowledge base. Okay, this knowledge base is then encoded and indexed in a vector database. And at the start of the generation pipeline, when the users prompts a query to the LLM, the RAG agent retrieves from this knowledge database all the information that matches a certain similarity score against the original query. And this is usually done with like several trials that are then like averaged upon. And then this new information that gets retrieved can be synthesized and can be integrated with the final response of the LLM. Now, of course, this approach, although it was like really interesting in the beginning, has some drawbacks. Like, for example, we have to make sure that the information that we are retrieving is actually aligned with the sense and with the scope of the query that we are giving the LLM. No, actually, this original approach didn't like resolve the hallucination. It actually introduced more hallucinations because beside the original query, we now have like this big database of knowledge that may be hard, for the model to properly process. And finally, the final part of the prompt augmentation pipeline needs to be very task specific. So each time you get into a new problem, you need to like restart almost from scratch, at least the last part of the pipeline. So this is why the original RAG framework was advanced by adding pre and post retrieval routines. In the pre-generation part, we have the indexing optimization. So, like for example, our knowledge database doesn't need to be stored as just like a chunk of text or like a chunk of data, right? It will be way better if we had like a custom data structure, perhaps like a knowledge graph or something more fancy to retrieve stuff in the optimal way. Now, not only that, but the queries that are actually presented to the LLM may themselves contain error or biases that comes from like the human input, right? So this is also something that needs to be cared, and this is done by rewriting an expansion of queries. Now, when instead we get to the post-retrieval stage, what sometimes is done is that the retrieved information is re-ranked against the new generated prompt to check how aligned it was with the original query. And another thing that may happen is not hallucination, but is a sort of context overload. Because again, we not only have the query, we also have this knowledge database from which we are retrieving our fact, our ground truths. And this may, and you will see that in the demo, like this sometimes will cause the LLM to start repeating itself multiple times because it has like too much context. So another thing that we can do is to actually compress that context. And we finally arrive at what is now state of the art in RAG technology, which is the modular approach. So this framework now actually become its own like full-fledged architecture, and the architecture is mostly organized into modules and patterns. I will give just a couple of examples because again the literature is quite wide in this. But like for example, with the modules we have the search module that is the one tasked with adapting the retrieval strategy, and so in particular the indexing optimization of the vector embedding database thinking according to the structure of the database. And most importantly, there is the memory module, which is what our workshop will actually be about. The memory module is what creates an unbounded and homogeneous representation of the knowledge base that self-enhance through iterating through the procedure, so that every time that we actually make use of the RAG technology, then the output is graded and indexing and the knowledge database organization gets enhanced after we measure like how good the new generated output was. Speaking of, other two modules that are popular to have in your architecture are the prediction modules that ensures the relevance of the information by filtering out noise. That is also something that may be in your knowledge database. And the task adapter. In the beginning, well, not the beginning, but at some point it said that like one of the problems with RAG was that for every new task you needed a different way to actually integrate the retrieved information with the generated output. And this is what the task adapter is here for. What patterns can we use? Well, the original RAG is simply this retrieve-read process pipeline that I started with. Then the advanced RAG introduces rewriting, retrieve, and read. And then finally we have some more like fancy stuff with generate, read, or self-RAG. But now in closing, we finally arrive at what our workshop is all about, and is the idea of soul engram. So an engram is a unit of cognitive information storage. And our objective is to develop the episodic memory submodule, because of course the memory module, again, is one of the biggest and one of the most sophisticated part of the RAG architecture. And in particular, we have the episodic memory submodule. Okay, so in order to do that, we start, for our experiment, we started with a data set of ethical judgment about scenarios that were deemed either example of justice or of injustice. And we start the experiment by embedding into our model what is considered to be a desirable state of mind, okay? And concretely, we simply started with the live, love, and learn paradigm that you can really think as a sort of like general vibe that you want your agent, whether it be like a chatbot or like more sophisticated humanoid robot, you start by embedding this sort of philosophy into it, and then what we do is implementing a query enhancement pipeline that retrieves from this data set of ethical judgments what are considered the most relevant, either aligned and misaligned. We actually choose to have both. So the scenarios that are more aligned with live, love, and learn, and the scenarios that are less aligned. So you can see they are more distant from the actual state of mind that we want to embed. The retrieved embeddings are then averaged out with the original state of mind as new information gets stored into the emerging engram, which is this unit of cognitive information that is the basis for the episodic memory submodule. And finally, we have the post-processing pipeline that integrates the new information into the generated text. And this is a very rough schema of like how our module works. You can think that the one on your right is just like a shortened version of what the whole memory module will be, and the one on the left is our actually episodic memory submodule that interfaces with the bigger main memory module. And that's pretty much it for my slides presentation. So I thank you all for your attention. Is there any question, or should I leave? Yeah, please go ahead.
I was just talking about it on that slide. I couldn't read it.
Oh, sorry, it's too little.
It's fine. I just wanted to take it.
Okay, yeah, sure, go ahead. Any other question? Okay, great. Thank you all.
Okay, so hello everyone. I'm gonna sort of talk further about this topic that Renato introduced about solongrams, but I'm gonna be much more focused on some of the theoretical stuff, especially with regards to something called hyperdimensional computing, which is my area of research. First of all, is anyone, well, go ahead, raise your hand, just like for Renato's case, is anyone unfamiliar with HTC? I suppose probably most people aren't. Okay, good. Then I'll give a very, very quick 1,000-yard view of it. So the idea is very simple. You want all forms of data to live in the same high-dimensional space. And so you're going to project all of the information that you're aware of into this high-dimensional space to achieve very useful properties. Now, for this presentation, we'll mostly consider binary hyperdimensional systems because they're relatively simple to get, but there are various other ones. So in the binary case, you're talking about spaces that operate on the order of 10,000 bits or so extremely high-dimensional binary spaces. And these are generally randomly generated. And instead, what you do is you use the randomly generated vectors to build self-encoding spaces. The intuition behind hyperdimensionality sort of mimics the relationship between quantum physics and classical physics, where when you have something like particles colliding at the quantum level, there's a lot going on there that is obfuscated when you zoom out to the classical physics level. And the hypervectors are very much like the classical physics, in which they're very simplistic, but once you have the back-end sort of relationships understood, at the high level, you get very simple operations that are very powerful. And as a result, what usually happens is that neural networks tend to operate at the minutia level, so the neurons themselves, and focus everything on that. Whereas hypervectors take entire systems into regard and their operations operate on the entire system at once, basically. So for all intents and purposes, our embeddings here, our vectors, are states of the brain, basically. And as such, you can understand the intuition, at least behind binary hypervectors, pretty easily. The ones and zeros actually represent whether a neuron activated or not at the current point. If you arrange the neurons into an array, thus giving each of them an identity, then you can look at, on average, what the behavior of the neurons are system-wide, basically. And that gives rise to a hyperdimensional model of what's going on in something like, let's say, the brain, right? Here's a sort of graphical representation of that happening. So you have some neural network at state A, you organize it into an array form, and then you say, well, the connections don't really matter. I'm interested in whether neurons activated or not as a whole. And then you study the neurons over time when you're doing a similar action. And even though there's variances in it, on average, as that color-coded there, they have a certain level that they revolve around where they activate a certain state. And so your goal is to basically learn that state of the brain, usually by aggregating the examples in section D. Go ahead.
Your clarification, like the whole golden gate grid thing that Anthropic figured out, is that the sort of thing that's like you're just trying to see like what. Sorry, but like you're trying to see what neurons are activating when you say golden gate grid.
Sure. Yeah. So yeah.
Oh, it's these 47 neurons.
Exactly. Except you're looking at the whole brain, or at least the part of the brain you're interested in with regards to that. And you're considering it that there's so many neurons, it's what's called hyperdimensional as a system, and get certain properties. Now, this model is a way of sort of thinking about, like, well, if I think of the number 3, what is going on in my brain? Well, it's fluctuating in many states around a certain, what they like to study in neuroscience, a certain level of activation in certain regions of the brain that they have in common. So it's sort of like that. But practically what you're actually doing is you're observing that most unrelated states in a high-dimensional system live within the standard deviations around 0, It's when things are happening many standard deviations away from 0 that you sort of say, wait, that's significant. And so when you do inference with hypervectors, you're generally operating on significances in the order of dozens of standard deviations. So basically you're saying, wow, it sure is unlikely that this vector coincides with this vector in such a way. Because since they're randomly generated at 10,000 bits or so, it's extremely unlikely two vectors will be anything other than nearly orthogonal, right? So any similarity is significant in hyperdimensional space. So, but like I say, you don't need to stick to the binary version. There's dozens of HDC paradigms and various things, Euclidean spaces, Fourier spaces, all sorts of things. Some of the most interesting work probably nowadays has to do with the Fourier versions of holographic reduced representations. But in the end, what you end up with in all these frameworks is some sort of an algebra. So it's a very simple system where you mostly multiply these vectors and add them, generally. And just real quick, this is an example of how you could do it. There's many ways to do it, but how you could do it with binary hypervectors. So you could use the XOR as your multiplication operation. You could use something called the consensus sum down here for your addition. A consensus sum is basically a winner, like a voting system where in each component, whichever bit is more representative is the one that takes all of the votes, basically at that level. So whichever bit's more common across the components, that's the bit in the output of the sum. So this is a sum that will give you back a single vector. And of course, I just had this here in case people are interested, but you can represent certain structures then using just multiply and add. So here are some examples. Of particular interest is records, because records can be used for inference. So for example, you might have many images of dogs, right? You can aggregate the hypervectors together with the consensus sum and then multiply it with a random vector that just represents symbolically dog. And then you can retrieve that vector, as I show here, for a simple multiply operation. And you'll get a vector that's similar to the dog vector. And it'll be the most similar one across your options. This blue square here is actually itself a hypervector that's just added up a bunch of these categories that you've learned from a data set, let's say. So now moving on to the topic of episodic memory. So this is actually something I've worked on before, specifically with navigation of autonomous drones, for example. We formed episodic memories from them using a DBS camera, because DBS is actually well suited for hyperdimensional operations because it's a very sparse signal. And so any significance in that space can be mapped to big standard deviations of significance in hypervectors. And so I basically encoded events from an event camera into hypervectors, which are represented here as a square of ones and zeros, basically. So this is your 10,000 bit vector, which looks a lot like noise because it pretty much looks like noise to a human. And then you aggregate the direction that you went with what you saw and aggregate the examples. And of course, the direction itself is a hypervector, and what you saw is itself a hypervector. You can recall one or the other at will. Some interesting things about this, we were able to compress our entire model into a single 8,000-bit hypervector, plus the memory to recall things that you might want, such as the velocity and coordinate hypervectors. So we're talking about maybe a megabyte big model that performed as well as a CNN. And the training time is minimal. Actually on a CPU, a single CPU, we were able to train in like a fraction of a second, mostly because we only needed 15 seconds of data before you reached optimal performance. The hypervectors couldn't really absorb anything more meaningful beyond that. So you would actually make a new model for the next 15 seconds, or whatever you want to do, and you can have many such models that work in tandem together if you wanted to, but these results are only with a single model. But why am I talking about this? Well, see, there's another paper I had a while ago called meta concepts, where I observed that if you have word embeddings, oh, go ahead. Sure. Yeah. Yes. Yep. Yep. It's a single vector.
Okay, so I guess the mapping is the interesting part.
Yes.
Need all these representations.
Yes.
Map them.
Yeah.
Doesn't that get big if they're very long episodes?
No, because this is the thing. All operations map back to the same size vector. So all operations are consistently the same amount. But what you could do is have many models, many different hypervectors, and that's where you get more memory if needed. So basically more brain states that you're interested in.
And then you're able to also decode back, because I assume you're using it for like replayers.
Well, it's generally a destructive operation when you encode, but if you had an encoding that's reversible, then natively it's reversible as well. So it depends on how you're encoding it. Generally, they're destructive because they aggregate, so they superpose on top of each other, and it's very hard to disentangle them unless you're very careful with how you design it. But yeah, it's possible to reconstruct. What you probably want to do is actually have it as input to another model that reconstructs it somehow from learning. Yeah. But the episodic memory here is essentially what the drone experiences as flying, right?
So is your operation continuity?
Well, it depends on the operations you define in that algebra, but for this case, you have the properties of XOR, which is commutative, right? So that part is.
I can't remember which order the.
You can impose that by encoding it in there with random vectors that represent order. So, like a vector represents 1, 2, 3, 4, and then you can recall the order if needed. So you can recall whatever information you want from the compressed model. You just have to have it there at the encoding time. And so what you find is that a lot of these hypervector systems rely on very good encoding strategies, which are generally neural networks. So the embeddings from neural networks are very great for hypervectors. Sort of why they're making a comeback now in this day and age. Hyperdimensional computing was sort of discovered in the 80s or so. So it's not a new thing, but it's definitely making a comeback because of neural networks. As I said, there was a paper where I noticed that if you just have the nearest neighbors of let's say a word to backspace or whatever, you can actually get a first order estimate of the manifold underlying the space. It turns out that you don't use the full space, the full Euclidean space in these systems. There's some underlying manifold that you're not aware of there. So when you do linear combinations, you might be sliding off the manifold. With a first order estimate, you're actually able to recall where things should be when you average them. So for example, in there, if you average U and V, you might end up here in the middle of the manifold when really you want to be on that geodesic line below it, right? And with this, you're able to do word sense disambiguation, where we've quadrupled in some of the cases the performance from random guessing to like pretty good performance with no training. This is purely a geometric computational system here that doesn't get trained or anything. You just need the vectors of the nearest neighbors. But the point of this is that you're isolating the context of surrounding words to help you figure out what's actually happening on the manifold. And our argument is to use that for the soul engram idea. Slightly differently than what I did in that paper, but let's consider the Euclidean case. You would project a vector P, which is something that you're interested in. For example, like live, love, and learn, as Renato pointed out in his presentation. Maybe you want an AI that focuses on those aspects of the world, as opposed to more negative aspects of the world. So you would project the embeddings representing live, love, and learn onto the embeddings of what's being experienced to sort of flavor the experience and isolate the things you're interested in. So in the Euclidean case, of course, you could just use vector projection to do that, very simply. In the binary case, XOR isolates differences between two vectors, so you can just invert the XOR and get the similarities, basically, that two vectors share, as an analogous thing to the projection. Now, in this paper on metaconcepts, I use vector projection to do what I did here, and so that's the inspiration for the Euclidean case. Now, what do you do with these projections, though? Sorry, my slides are out of order. This is the slide I wanted next. So what do you do with these projections? So you flavored your experiences and changed what they look like. Well, now you have to summarize your experiences into one entity here, right? So giving a training set of experiences, you flavor them with these projections and then simply aggregate them together. With Euclidean vectors, it's pretty simple to do that with averaging, but you could use a more sophisticated thing if you want to. For hypervectors, you could use consensus sum as the operation to do that. So out of these many experiences, you get one embedding that's the same length as each of the experiences that summarizes all of them, but they've all been flavored in a particular context. So it deviates from the true average in the direction that you're interested in, specifically in the direction of live, love, and learn, right? And so now when you do lookup in a RAGS-like system that Renato described, you'll find experiences that have to do with live, love, and learn, right? And if you present that to the LLM before you query it for an answer, then its response will actually be flavored towards live, love, and learn. So that's pretty much it. Some preliminary results, we've tested this on synthetic data sets, made mostly by constructing random vectors and sort of making complicated manifolds out of them, to see if you're reducing the semantic distance between the episodic memories and the sole engram you're interested in. And so far, we've been able to do that by many standard deviations of significance, especially with hypervectors. When you apply it to concrete examples, like Renato's going to do in the demo, he'll show later on, qualitative analysis shows improvement of relevancy too. So you'll see that the responses are more in line with, let's say, live, love, and learn. You'll see that as an example. However, we are sort of sorely in need of a standardized data set to test these ideas on. So that's sort of the thing we might be interested in now in order to do more work in this direction. I'll leave off the presentations with some future work and interesting ideas that you could do. Multimodality is one that jumps to mind right away. Because you can flavor what the LLM is going to say with experiences rooted in sensory perception. And it just so happens that hypervectors are excellent at multimodal fusion. This is another one of my papers where we were able to fuse different networks together at a symbolic level by simply learning what the vectors predict as a hypervector and aggregating those together with IDs for each vector. And it turns out when you do this, they work together. And in that paper, we were able to boost performance by a relative 10% for free. Even though in that paper, this DTQ network, all these networks were by the same author, by the way. The DTQ network was state of the art and was far better than any of these, meaning that there was something to learn even from worse neural networks, simply because what they learned is fundamentally a different modality than DTQ, right? You can also do this with neural networks. So this is another paper where we show that you can take the outputs of neural networks, the embeddings, and convert them directly to hypervectors and preserve almost all the information from the network's prediction, and then fuse networks together in the hyperdimensional domain. And thus you had a multimodal system in one hypervector. Now take these ideas and project them backwards into the LLM through the RAGS lookup, and voila, you have perception flavoring what an LLM is going to say. So some notion of an embodied AI there. Another idea, lifelong learning beyond looking up experiences directly, such as through RAGs. So instead you reconstruct your episodic memory from the episodic memory itself. Sort of how the brain might reconstruct what you're seeing inside of it. You don't actually see what you're seeing, you see a reconstruction of it in your mind's eye, right? So something like that. And lastly, using the context vectors of the LLMs directly, which is something I'm very interested in, where you actually take the embeddings from the LLMs at the token level, and you do these projections on them, so that you don't actually need to introduce any lookup or anything. You're directly using the LLM as is and flavoring its output at the neural level, essentially. And you can do that all with hypervectors as well. So that's the end of the presentation. Here are the references that I used here in the presentation. Any questions? I saw your hand up first, so I'll go with you later.
Sure. I think the middle point is way harder than maybe how it sounds, because reconstructing, my group has done that. We also work with holographic declarative memory, which is kind of like one of the, you mentioned holographic.
Yeah.
It doesn't work quite well.
No,
Constructing things in order as well. So temporal memory, we were trying to, actually it was in the AGI paper 2 years ago, in addition to a complementary clock cycle. We have this issue that reconstructing like episodic replay and reinforcement learning, which was like argued, it's very difficult problem because that reconstruction method doesn't work very well.
So fortunately, you can actually, like I said, encode at the encoding time the order things happen symbolically and then recall that. Of course, the issue is that there's a limit to that because how many symbolic representations do you have for order? Now, with hypervectors is a paradigm called multiply, add, permute, where they use a permutation pattern to get a symbolic representation of the next thing in the sequence. And with that, you can actually just permute the vectors and get like positional replay of experiences. But of course, one issue with permutations, even with 10,000 bits, there's actually a finite number of steps you can repeat the same permutation before you get the same beginning vector back. So there's that issue there. But it's actually quite nice when it works, you know? But of course, even humans probably have trouble recalling exactly the order of things throughout their whole lifetime. So things are probably organized into bite-sized replays, even in the human brain. So, you know, one answer is to just use bigger vector. So you can always go bigger. That's the nice thing with hypervectors. Bigger is better generally up to a certain point, where you've squeezed all the juice out of your encoding. So what you're actually interested in hyperdimensional computing is good encodings. It's a very encoding-hungry paradigm. You have questions?
Yes, so my question is about hypervectors in general. So I haven't understood everything before, but when I try to like understood hypervectors at home, like I look at some articles, I have general impression that like claim of hypervectors was that okay, more or less you cannot do something maybe better, so you don't propose to do something like different, but you propose to do something faster.
Yes, it is very fast because of the algebraic operations.
So my question is, with what you just presented, do you propose something different, like it's something which you cannot do by other tools, or you propose something which can be faster?
So the issue is when you say other tools, the first thing everybody thinks of is neural networks. The problem is, as I've shown, neural networks are hyperdimensional systems. Their embeddings are. Every single layer as it projects is itself a hyperdimensional system. The only issue is it's a system that you don't know the algebra of. So generally the goal is actually to learn the algebra behind what your AI is doing so you can reorganize through algebraic operations instead.
Yeah, but it's like in theory, I'm talking like okay, maybe you could point out an article, because all articles which I've seen was like, was this ideas that were interesting, but final results was like, say like not better than other results.
Yeah, you can always come with. Yeah, go ahead. Sure.
Okay, so, like, this is something that we actually spoke at the HTC workshop that we had back in Valencia, and like one of the things that perhaps in the literature is misrepresented is that HTC in a way claims to be like an alternative to, I don't know, deep learning, machine learning, or lo-fi, or whatever you want. HTC is actually a functionally complete framework, which means that you can do like mostly everything that you do in other framework, and this includes, of course, neural network. This includes large language model, transformers, and what have you. It is, of course, not clear what is the most efficient way to do so. So what happens then is that, like many papers claim, okay, we can do this, but then the result by itself, okay, it won't beat OpenAI, okay, it won't beat DeepMind, but again, that's not the point. HTC is not an alternative to deep learning. Rather, it is a sort of like,
fusing it.
Yeah, it's a fusion of different approaches because you are in this again functionally complete framework in which you can just glue things together because it's a one sorted framework, okay? Everything is an hypervector, so everything can communicate.
So what you can do, like in this paper, is win by doing consensus. I can take whatever best model you've made, like an amazing model, state of the art. I could just take the top 10 state of the art models, fuse them together, and beat you. That's the thing. Now the trade-off, of course, is you have 10 models working and taking up more memory and stuff. Would it be better to have one big model? Yes, but as you see with LLMs, it's quite expensive to get that big model. And more it seems like you want a more modular approach where you have some models that stay the same, that are small and bite-sized, and you essentially take a multimodal approach downstream to actually get these bigger models that get state-of-the-art performance.
So, in this blog, you present approach how to use Hyperdimensional to combine the
Yeah, and what's cool about this is all the same author's work. So I beat the author's state-of-the-art, which was DTQ, by just using his previous work as well. That's the irony here. And it's quite significant, as you can see. That means that 7% of the examples were just only solvable through the other two neural networks. And what's impressive is that when you fuse them together in the hypervector form, it actually like overtly prefers when the model is better suited for that particular example. So it actually like overtly prefers DCH for one of those 7% of the examples versus DTQ. It actually upvotes it quite a lot, and it gives it a bigger vote essentially because of the alignment of the projections. The projections just align so much better with DCH for that example, and with DTQ they're more orthogonal. And that's why it upvotes and picks and chooses it that way. So yeah, hopefully that answered your question. Yeah, you can get better results, but you're sort of doing the cheating way of consensus, like models. So, you know, it's a sort of a, I guess, like a lot of people consider that sort of like not fair, right? You should just use one, but yeah.
The initial play that you can do something possible before
Yes. So generally, as a rule of thumb, you can get for the same level of performance with a hypervector model, you get a reduction of energy costs, for example, of like about an order of magnitude, so about 10 or between 8 and 10 times less energy for the same performance of a neural network. And it's very good for swarm intelligences where you want like very simple AIs in each of these like onboarded, you know, drones such as this example where we use like, you know, drones to do this. You don't have like GPUs that you can stick onto the drone because it wouldn't be able to fly then, right? So it works very well for that. Yeah, generally you get energy reduction or speed up, or some combination of both, depending on, you know, how you design the architecture. And yes, these models are very nice for explainability because they're symbolic, so they can recall the symbols that they use to actually justify the results. So you can see why it thinks, for example, that DTQ DCH might be more relevant for a problem in DTQ. You can see it at the symbolic level if you wanted to. You can actually analyze it. So it's a little bit less of a black box system than an AI. One very interesting thing that I've been trying to work on is sort of like a knowledge distillation framework where you could take a neural network and distill it into a hypervector model, and then the neural network essentially becomes explainable as a result. So yeah, there's a lot of interesting things now happening with hypervectors. Some of the most recent work that's most popular is like the Fourier reduced holographic representations, where they're able to do like image recognition by like doing all sorts of warping of you know, objects, and the system will always recognize it without having to learn actually all those orientations because of it's abusing Fourier, like the spectral representations, to do that. It's like a neat trick you can do with Fourier transform natively. So interesting stuff's happening, but yeah, for this work, we're mostly interested in the fact that you can always project to a bigger space and take up more neurons without changing the base thing that you're working with. So you can have more episodic memories by just increasing the length of the vectors. And actually, oftentimes, you can do that without disturbing the existing models. You can essentially add neurons and fill them in with new experiences without changing anything. If you notice, most of the operations go on the component level. And so there's not too much mixing of information unless you're using something like the permute framework where you permute the bits. So.
So you take these, in this picture, you have like 3 models.
Yeah.
And their output vectors are, say, the same length. And they're,
yes.
And they're telling you about some information. They're
yeah.
practically the same thing.
And I made the vectors obnoxiously long.
It's
yeah.
8,000, whatever.
Yeah.
8,000.
Way longer than they need to be, because these produce hash codes that are usually like 50 bits.
So we get these big, long bit vectors.
Yeah.
And then we multiply them by something that tells us who's who.
Yeah, a random vector.
A random vector telling us this one's for model A,
yeah.
this is the model B. Then we add those numbers together.
And a consensus sum operation, so you get back another vector, same length.
Consensus sum is the mode.
Yeah.
Right?
It's the best vote, essentially, per component, yeah.
And then that thing, okay.
We'll recall the solutions that each of the networks, because each of these.
But you don't use that as your output to the user, right?
No, yeah.
That thing, yes or no?
Yeah. So
even though you multiply it by weird numbers.
Yeah.
And that, okay.
Yeah.
Can you explain?
So what you basically say is you search through the models with the symbolic representations of them. You go through all your models, those random vectors, and see which one's actually producing the best match for your inputs. Yeah, so you might have a Hamming distance across all 3 that one of them is like very.
This is not just I typed in some query and I got an answer. I showed a picture of a dog and it's like trying to tell me whether it's a dog or not. Like this is.
Yes. This was a data segment for like a hashing, which they have that too, that you want to identify what the image is from a hashed representation, but also rank it in similarity to other images. So this is preserving the rankability as well of images. If that helps. I don't know if that's what you're asking.
Well, I'm just confused about how multiplying the answers by random vectors and then adding them to a mode.
Yeah, so for that we'd have to go back to the intro where I talked about this, the hyperdimensional inference layer. So this is what's being used there. Very simply, when I see a new example, I purposely color-coded it to be purple because all the examples of the dog are similar in some way. So we'll call them purple. And then the dog identity vector that's random is this deep purple. Now when you XOR the blue model that's aggregated all other categories together into one hypervector, when you take that hypervector and probe it with an image, a new image, what you'll get back will be very purple looking, essentially. You'll notice that actually the bits don't align between this and this. They can be off quite a bit. Actually, hypervectors are very good at noise tolerance. You can like flip a third of the bits for 10,000 bit systems.
It's kind of magic that when you finally get what it's saying, you're like, oh, now I get my.
Yeah. It takes a bit of chewing on.
Okay.
Which I highly recommend this first reference, Kaladharasarguda. He's sort of the guy that spearheaded this. He's the guy that invented sparse computing, basically, at Stanford. But he somehow dipped his toes into the AI space and used a lot of what they use in that field, like cryptography and stuff. These are essentially cryptographic sort of arguments that are happening here, right? Very similar to like what's happening in Bitcoin and stuff, where like once you get the correct thing to ledger, well, it all works, but if you try random stuff, it's not going to work, right?
So two partial questions. So one is, are you not working with so the hypervectors? There's also complex representation.
There's also complex versions of.
Are you not using those?
No, for my thesis, I'm sort of focused on just like what can you do for a general intelligence using hypervectors. Like my argument, my thesis is that this is a good lifeblood for AGI, so a communication system for an AGI to communicate with other parts of its system. So I'm just saying that hypervectors are good, and the best way to do that is to use binary because they can aggregate anything into that space pretty much.
So then, if you're not going to use the complex representation, which comes with some drawbacks, my other question, the follow-up question is, how big do you tend to make these vectors? Because you see, it sounds like you're getting, maybe complicated, you're using an element-wise multiplier.
Yeah.
So you get speed and compute, but as we know, maybe in computer science, the trade-off is memory versus speed. So for your case, bigger is better, but there's a point where I can't store a 10 billion dimensional vector, which would give me.
Right.
So how big do you find you end up needing? And what's the scale more proper?
Traditionally, once you hit like 2 to the power 13 or 14, you start getting diminishing returns after that.
So it is actually true.
Well, it depends on how difficult the problem is. The more difficult, the longer the vector. But a lot of these like machine learning data sets are actually not that difficult for 2 to the power 14 if you have good embeddings. They're salient and give you the information. So the better the embedding, the smaller the vector you need. That's the real trade-off.
Do you foresee then a potential conflict as we get too much? Because machine learning is arguably not the hardest of tasks that humans can do.
Right.
As we work towards, forget about AGI, just human level intelligence. Do you foresee then a problem with the scaling properties of HTC?
Not really, because the way I interpret it is you can think of the hypervector as a subcomponent of the brain, and then once it says something, it'll project what its results is to the other parts of the brain, right? So really, you can have many hypervectors in one system, and actually one of the active areas of research is how do you have such a system while still maintaining a lot of the nice properties of hypervectors, such as lifelong learning capabilities and stuff like that, the generalness of the representations. Yeah.
Perhaps an assembly of hypervectors.
Yes. Which is why my argument is it's a good lifeblood for an AI in my thesis, basically. So it's the thing that it's used to communicate, but it might not be the system itself.
Peter, thank you. On that theme, this is something that's ever since I became aware of this space a couple years ago, I've been sort of wondering or playing with the idea of like, well, why not push this representation deeper into the stack of these features rather than
Yes.
kind of make a deep neural network that does have robustness to kind of start forgetting using these primitives in some way, mixing with operators. And I looked at the literature a couple times and didn't really.
It's a hard thing. They're working on it. They're working on it. It's a hard problem because it has to do with the embeddings and the encoding structures. So really you have to be ingenious at that to get like what you want. But roughly, you want to push the hypervector system, as I pointed out in this slide. You want to push the hypervector system as deep into the brain as you can.
Yeah.
You want to use, like, for example, your eyes. Well, they're hardware essentially. So what they encode is gonna be unchangeable natively, right? And actually, there's a cool paper that showed that mammalian eyes actually encode what they're seeing into about like 10 to 15 sparse signals. Some of them we recognize. And then the brain just, they pass off to neurons and somehow they can reconstruct what we're seeing from that. So, there is an argument for the hardware part and also the early neurons, they don't change much in what they do. As you go deeper though, that's where you can start like mixing these representations actively however you want and don't suffer any of the consequences than if you did it earlier. So you kind of want good neural networks that do very specific things and then pass that off to hyperdimensional systems or something that's more and more hyperdimensional as you go deeper and deeper into the framework. And really in the brain, eventually all that data gets projected back to the sensory signals it came from. Like when I see something, I can also envision smelling it, right? So really it's not even an argument of deep, but there's sort of like a core area and then it all comes back to the individual senses, probably also going slowly and slowly into a more hardware representation or like a neural network-like representation. So yeah, it's a hard problem to think about, and already there's a few people working on it. But yes, it is something people are trying to do. especially with the Fourier reduced holographic representations. That's where something like this is happening, I think.
Maybe we'll chat about it later. Something I've been thinking about.
Sure.
It's been bugging me.
Okay. Yep.
We have two questions from the live stream.
Sure.
Actually. So one is, does HTC allow you to use multiple senses to form a single image of what's happening, which could then be used to build a simulation of what's happening in an agent's environment?
Yeah. That's it. It's very much like that. The proper way to think of it is that all the data exists in the same space and therefore has to space itself out through self-encoding, self-encoding encodings that you learn over time, right? So really, since everything is generally random in these hypervector systems, like random representations for everything symbolic level, what really matters is how you do the operations on them to get more complicated structures that sort of find their own location in the space. So yeah, all these modalities live in one space, and in theory can be reconstructed by probing the proper space. So that's what's happening when you do something like here, where I XOR with, what I could do is XOR with the dog vector, the random dog vector, and get back the aggregate here, meaning this like conceptual thing of what a dog looks like. But I could further probe with specific images which of these examples that are aggregated are actually relevant to a specific dog image, right? So you can, in this way, slowly reconstruct back what you actually saw by just trying all the options, which is probably going to be done through like a brute force, like neural network structure, right? So, but yeah, you could reconstruct your experiences, and maybe that's what's happening in the brain too, when what you're seeing gets reconstructed from what the eyes actually experience as sensors.
There's also one more. You're seeing lots of classification uses. What other tests can you use?
Oh, you can do regression as well. One framework that's very good for regression is the Fourier reduced holographic representation, which is why they're able to like manipulate images and all sorts of transformations and still find them, because it's actually a continuous space in the Fourier domain. So you can do regression. You can do anything that ML does. It's really just limited by the same things that ML and GoPy and stuff like that are limited, because inherently you're using them in these systems, right? Encodings are done by every neural network. CNNs, convolutional encodings, are just encodings that look at the data a particular way, right? So, it's the only limitation is where we currently are with AI, basically, in general. Good. All right. Thank you so much, everyone.
Okay, so I'm not sure if this was not working so well earlier, but so we have a scheduled break for coffee about like 10 minutes ago, but I don't know. We have David Hanson has joined us, so I don't know if David, we did our intros actually moments before you arrived, but because we got such a late start, but if you want to introduce yourself.
Sure, absolutely. So I'm David Hanson, the founder of Hanson Robotics. I have a background, an interdisciplinary background doing robotics powered by AI to interact with people, and then also academic background in neuroscience. And I'm very interested in the nature of consciousness and how we can create conscious machines. So I have a team of software developers at Hanson Robotics, that used to be sort of fused with a lot of the development team at that is now at SingularityNET. We sort of spun that out, if you will. So Ben was my chief scientist, and so we have similar goals that are aligned. Our goals, of course, being a robotics company, do focus somewhat on physical embodiment for the artificial intelligence to enable the robots to physically interact with the world, socially interact with people. I am very excited today to talk with you about some of the ideas. I think the rest of our team on the panel have been discussing various angles of similar concepts, how episodic memory and motivation can interplay with a dynamic learning process to give rise to something closer to artificial general intelligence, becoming potentially generally intelligent, conscious, self-evolving, maybe living. And then evolving, that it would mean not just adapting, but also becoming more sophisticated and complex over time. Approaching our super intelligence is, of course, the next level of goals. So I'm excited to show you a few slides about what we're doing, and then I'd like to patch in a couple of my team members. We have Winway on the line, but we also have a couple of other team members that we're collaborating with on here. And also a lot of these ideas have been in exchange on a couple of little working groups. AGI Now is a little working group, or BGI, Beneficial General Intelligence Now, and then a little group that we call Sentience Quest. So I'll introduce some of my team members when the time comes, but I'll just throw out their names right now. Winwei Wang, Vitas Krishunas, and Zan Varko. So thank you. I'll switch the output from this computer to my computer. Okay, cool. So just give me a second. And I apologize for the fact that we got started late today. My flight was delayed. There were complications, but we're adapting because we're generally intelligent.
Should we take a short coffee break and then we can get this set up?
Let's do a coffee break. Yes. Thank you.
There's a Starbucks in the library, but I'm not sure whether the library is
Yeah. Okay, let's see now. Make sure. That might be just good.
No, that one error is the one that I told you, like it happens every time because there is a library that it uses at some like very nested point in the Eigenspace API. They have this library which is PyArrow, and you have to have the right version of it so that the API provides centers. I'll be right back, or brief.
So how are my children?
Good. It's been crazy, like scramble to get first.
Yeah.
Weeks now.
How's it working?
Going good. I mean, it's you.
Robotics is a pain in the ass. Just have to say it.
Yeah. But it's going well. We're having all the little victories.
It's because but anyway.
No, the legs are like heavy rounded.
Yeah, this is a pretty classic strategy.
This week you turn off the microphone.
But essentially just
Or I can turn off this speaker.
put it into business. Yes, you should.
This microphone here is actually like all the things.
Carry over the meeting and stuff. It's just normalizes the time.
There's actually.
And then you do essentially with the linear combination of the hypervector representing the value, and the hypervector representing the shape of the function. And you multiply together. That's what it is. And then add it to the next one, and the next one is here essentially supposed to get out. A lot of the goals with hypervectors is to distribute.
When it comes time to like dive into our code and architecture.
So this all the ones with hypervector experience. No, that's self-encoding. This is self-encoding the space. Even though technically the bins are random. Not really the beginning of every one and one random. But otherwise, the raw representations.
Oh yeah. Thanks for taking the lead on that.
But I don't think it's but if you miss the beginning, somebody talks about this a little bit, so so we got started usually high enough to hold any kind of data. Those make that space big enough. I'm gender as well as like single characters, single audio, right? So it's big enough to handle the geometry. So yes, things have that space. Let me know. And here I'm going to do a projecting low dimensional data. Oftentimes I think it was hard to see. I'm going to focus on binary numbers here for each thing, but there's complex, there's real, there's warrior, there's just as long as it's high dimensional. Technically, neural networks are you just don't know the algebra. You can learn it through. The slide I showed you before, for that later.
Oh no, I just got.
It's learning that. How the
Oh yeah, do you know Yosha? But it was, everything was just like, yes, this is amazing. And then wrote to you saying that we should definitely follow up. Oh
at some point, and you and I had said that in break what that correct, that should cost you
yeah.
what you're interested in getting that. So I think we should chat more at length, probably let you do your talk. Ready?
Okay, I'm actually all ready now, so I'm going to just put it on the share screen, and then pull my presentation up.
And for these, you have to use the H. The negative one is when the one is something between interpolations or transforms. So that it depends on you can also make the pilot you just
Just leave this.
There you go. That looks like you're and as a result, the analogy between
Yeah. For anybody who's online listening, we'll be back in about 10 minutes. We're in the middle of the coffee break, so hang tight. We've got a lot of exciting things to discuss, and we would love your involvement. Thank you.
Yeah. Yeah, I'm from SingularityNET. I'm also yeah, so it's like being kind of like an AI development sandbox. So yes, that part, that particular part, it's kind of like hyper-automatic. So it takes the information from Big fan of your work. So happy. Yeah, I see that tomorrow you're also going to looking forward. Yeah, well, the idea is that we're trying to actually my what I do is by always involved very because there's no legal like enterprise very yeah, actually we published a paper very good like how to essentially generalize medical into what we call social yeah, so there are like two ways. Like one normalization was presented by
Yep. Thank you.
Half an hour to my break window. 12:15 is my break. Yeah.
Well, I'm good now.
Okay.
Thank you.
So to me, it has this very like mental essentially a framework about the competition yeah, no, we don't need it. It's just really like why. Again, it was very funny because yeah, like they asked me where would you put this in I was thinking some models of computation like somewhere around there. When did I realize that the framework itself keep the conversation. Get back to your quite small and it was like an article which showed that essentially do whatever you do with like 5
Okay. Okay. Ready to go? Yeah, please do. Sure. Okay, hello everybody. Welcome back. I am going to jump into a little slideshow that shows our work and where we're going. I'll probably talk for about 15 minutes and then turn the presentation over to my team, who will then share more details about our software architecture, our current work, and where we're going next. So this is, for me, about the pursuit of living artificial general intelligence, meaning that it's spontaneously self-adapting, it's able to survive, it's motivated and driven to want to live and to learn about the environment, and it appreciates the environment. And so you'll hear the term live, learn, and love. Live, love, learn, right, over and over again. This was a phrase that that came up on one of our panels at the Beneficial Artificial General Intelligence Conference. It's a concept that I've been playing with for a long time, this idea of existential information ethics, that I think is at the mathematical and physical foundation of what living systems can do. It is a required pattern for something to live. It needs to want to live. It has to be motivated to live, and then motivated to love the environment, to love the ecosystem that it's in, the systems of information. It needs to be motivated then to learn by that kind of love of life and love of patterns. So these are all aspects of what I call the pursuit of living artificial general intelligence. Pursuing the theories, pursuing the practice, and then bringing this kind of being into existence. I think if we do turn to these first principles, if we can identify those first principles, then we're much more likely to be value aligned with the AI. We'll have a strong theoretical foundation. Things will accelerate, and then we'll accelerate in the right direction. That will be good for life. Some of the elements that are absolutely indispensable for any living system or AGI would be episodic memory and motivation. So I'm really happy to work with you on this workshop today. I have been developing these kinds of robots as works of art and also works of engineering, kind of philosophical quest to explore what consciousness is, and also a quest to create computational consciousness. And my teams on this have been pretty small. Some of the members of the team are here who have been part of Hanson Robotics, not currently are with Hanson Robotics, but are in the community here. So greetings to everyone. This is an example of a robot that is not conscious, but is able to see the gesture. So that example of this video, which was directed by Stefan Vladimir Bugai, who also was part of this community. It did use face tracking. So it used, it could see the face head gestures and then mimic those gestures. And so this artistic crafting of the AI can enhance the human experience and then create a kind of co-evolution of the AI with humans. So I think of this as artistically enhanced artificial intelligence. I also have another term for this, which is autonomous robotic fiction, or ARF, ARF. Just the idea that you have some autonomy that can be artificial intelligence, rules that you've crafted, you have a robotic embodiment, and then you also have this element of the human narrative, the human aesthetic that can facilitate these kinds of interactions. So humanizing AI and robotics lands in this context
in this day and age, you've all seen many of these kinds of humanoid robot products. It's interesting that it comes up with an arts cap. Okay, so here's the latest atlas. You also can see the latest in many of the other robots, Figure and Optimus Prime. So I'm not going to spend a lot of time on this. It's just, you know, that humanoid robots are coming. They have a certain aesthetic. I think they're beautiful, but they certainly aren't designed for the kind of aesthetic communication with people. So I could, with my mixed disciplinary background, I think I mentioned some of the technical aspects, but I also studied film. I was a sculptor, a figurative sculptor. I worked for Disney doing animatronics, and you know, so if you go to Tokyo Disneyland, Tokyo Disney Sea, you'll see some of my things. There's a giant a number of giant animatronics at the Winnie the Pooh's Honey Hunt. So I really love aesthetics. I love the power of aesthetics. But underlying all of that work is a constant thread since I was a kid, late teenager that is. I felt that artificial intelligence would eventually change the world. And that, and so I was really pursuing this fusion to create this kind of symbiosis between the future of artificial intelligence and humanity. It is an extension of nature. I think we can all accept that human civilization is part of the natural universe. It springs up from this. But the question is, how do we harmonize our technologies with our biological nature? And so this is why bringing personality to these agents, I think, is really important, because we are evolved to communicate using facial expressions, gestures, narrative, story, the spoken language. Now AI is starting to do quite well with spoken language, but the nonverbal presence in a full interaction, AI and robots haven't done super well. So we've created what we call the Sophia Utility Platform to explore that kind of social engagement with robots. And so communicating with humans on human terms is actually good for people, and it also potentially can gain the kind of interactive data to train AI on experiences, basically raising AI in the human family. And this can allow us to converge on trustworthy AI. I don't think that it's the answer by itself, but I think that it can help. So some of you may have seen Sophia in the news, but maybe you weren't aware that there were many other robots. Most of these were during my PhD research, some shortly thereafter. Some of the latest robots are built on the Sophia platform. I took the knowledge from robots like the walking Albert Einstein robot made with the Hubo group, and the Diego-san robot that you can see there, the Philip K. Dick android Dina 48. All of the knowledge about how to make facial expressions, make the materials lightweight, all of this went into the Sophia Utility Platform, but also the artificial intelligence tools. We were using early large language models with a technique called latent semantic analysis and latent semantic indexing with a bunch of linguistic rules layered on top. That was in conjunction with the University of Memphis, Art Grasser, and Andrew Olney. So that was 2004, 2005. And then we were doing many things with knowledge models in atom space using a system called Cogbot, which was actually a project that was running parallel to OpenCog. Ben Goertzel advised it back in 2007 and 2008, and it was using an atom space that was derived from Psych.org, Dublin, Oxford. And so these robots could have open conversation. We won the first place prize for open conversation from AAAI. They weren't spontaneously learning. They were not generally intelligent in any meaningful way, but there were platforms for researching that, and they still are. So
this integrates arts, physical hardware, mechanical engineering, material science, and then you put all these things together in the right way, and you get this full range of facial expression simulating every major muscle in the face. And this was 2005. And it was lightweight, low power, so it could fit on this walking robot body. I'm just focusing on this Albert Einstein example because it was using the auto tutor from Art Grasser's work in Andrew Olney, and would have a full open conversation while tutoring high school physics. So walking Einstein, tutoring high school physics, 2005, that's, you know, quite a while ago. I think now, of course, we can accelerate our progress in all of these different areas that we've explored. Sophia, the history of her involves not just the science and engineering platform, but also her as a kind of celebrity. That was intentional, but not the only purpose for her. She is a utility platform. So, so we have some mass production. We're now on number 60 and 61 of the units of Sophia. So we have these other models, but we also have Sophia. So we've gone through multiple generations. So we have a dense array of sensors, force feedback on all the joints, self-navigating base. So, and then we have an interesting SDK that integrates a lot of things, robot operating system, a lot of sensing and perceptual processes, LLMs, also symbolic artificial intelligence as well. And we've been interfacing that with SingularityNET and OpenCog here and there along the way, keeping those bridges open. And that includes through our collaboration on Awakening Health Grace robot, which I appreciate very much. So the open hands, a lot of this is open source. This is Sophia's Open Arms project, which you can see here doing various grasping and manipulation tasks. So that's open source. And then we've also been working on some legs, walking legs here, so Sophia walking. Now these particular legs that you see walking are the DRC, Dark Robotics Challenge, Hubo legs, in conjunction with KAIST in Korea and the University of Nevada, Las Vegas. But we've been developing our own legs that then are supported by a mobile base with wheels. So we have a working version of that we're shipping to a client. We've been experimenting with that and showed that at the conference AI for Good last year. So so we put all these things together in a toolkit, and some of the examples that you see here, like the logical mathematical intelligence, was OpenCog back in 2016, and then some of these verbal intelligence, naturalist intelligence, that also is the OpenCog, which became SingularityNET. But we've been able to show many other aspects, all integrated in one holistic platform, and we call this the Hanson AI SDK. And so it runs local or on the edge, can run with consumer devices, mobile, and interfaces with the cloud. We've been designing this also in conjunction with this, which is the OpenCog motivation action selection workflow, which we adopted for part of the architecture for the Hanson Robotics. Now, we'll go into more architecture later, but I want to ask a few deep questions and share with you some of what I think would be foundation concepts for where we might go with this conversation. Why make motivated episodic memory? And it comes down to this, you know, where does life come from? Where does intelligence, consciousness, creativity, where do these things come from? So information we know can't be created or destroyed like energy. We're just all made of energy and information, and that's it. Our matter is just a kind of informational pattern of energy. E equals mc squared, we're made of energy. And so what defines the human is not necessarily the matter itself, the molecules, but actually the patterns that make us human. That's what makes our minds work. So in a sense, we're just 100% software. We're just nothing but those patterns. And those patterns can exist in our physical bio-wetware, or they can exist digitally. We don't know, of course, if we are actually analog and quantum computers and maybe some other kind of computing. We might not just be digital computing. But we are, from a theoretical perspective, made of information. So, so then the question is the meaning of that information. What are the patterns, what Bateson calls the difference that makes a difference? Where do these patterns come from? How do these patterns manifest into existence? Not all potential patterns come into play. Some are latent, some are just potential and never will be brought into play. So the mystery of emergence is central to the questions of general intelligence and the future of intelligence. And there are many examples of creativity and general intelligence in nature, and octopus is generally intelligent with a very different neural architecture from ours, corvids and bird avian intelligence. And so we think of human-like intelligence. Human-like intelligence and creativity actually shares some abstraction with these other species. And we're starting to see many of these architectural components be put into brain-inspired cognitive architectures, into deep reinforcement learning, and we're starting to see very interesting results, but none of them are yet fully what we might call alive, where they are self-reprogramming, subsisting, curious, spontaneously evolving. So I want to propose some ideas that might be useful. One key idea is what I call existential pattern ethics, and some of you who've known me and maybe seen some of my papers might be familiar with this term, but it's not a common term. What do I mean by this? Existential pattern ethics. What I mean is that a priori, for an organism to live, it has to have some system of drive that makes it want to live. And so there's some patterns in there that value pattern persistence, pattern existence. And it doesn't necessarily mean the same pattern. It can be a dynamic pattern persistence. It can be an astable oscillator, but it has to be able to persist. And so it requires memory. It requires a bunch of other features. It requires motivations. It requires the processing of the memory as episodic memories with motivation. And so in this context, the information is defined based on its meaning, not just the presence of information like Claude Shannon's information theory would. So it is the functional patterns in a context, and that is intrinsically valuable to a living being, not outside that. So in other words, ethics is at its foundation about life wanting to continue to exist. And that's encoded in every cell, it's encoded in our molecules, in our biomolecules, it's encoded in single-celled organisms, multicellular organisms, it's encoded in our nervous system. It's where our sense of right and wrong comes from, I propose. And it is also what drives our intelligence. So our motivation comes from this biological point, and it drives up to our cortex, neocortex, it is new. And then, and our thoughts, our reason, our rationality, our motivation to learn about the mysteries of the cosmos are entrained with these deep drives, very deep. So, and so this is a mathematical predicate. It's required that this exists, that this kind of drive, this deep drive exists. So so good effectively is defined as the creation, preservation, and ethical use of information for the persistence of information. And the destruction or inhibition of information is bad. Of course, there's necessary evils, if you will, in natural evolution of information. So Darwinian evolution creates a kind of paradox where some organisms have to die in order for evolution to proceed. But now we're at a different point. We're becoming more efficient with preserving information. We can store the data for longer. The smarter we get, the better and more ethical we can potentially become. So we might be able to exceed the natural ethics of Darwinian evolution and start to kick up to another level of ethical behavior that I might call wisdom. So live, love, learn comes from information pattern ethics. So then I'm proposing that the biological evolution shaped this kind of information processing in the human organism, and it will shape it in our AI. Right now, AI is a cognitive prosthesis, an augmentation of human cognition. It is not its own kind of species, if you will. It's not yet its own branch on the great tree of life, but I believe that it will be. And I believe that humans augmented by it are becoming a new kind of branch on that tree of life. So here I'm trying to define mathematically the evolution, the ethics, and so you can see here some of the math, and I'm happy to share this. This is pre-publication, so this is the first time that some of this math is presented, but happy to share this with you. So I'm proposing these mathematical axioms that would drive existential pattern ethics, and underneath that, and from that we can derive many of the other things. We can decide what is an ethical system or what is not. The more that an intelligent system is able to be curious about, understand, and assist the web of life, the more ethical it becomes. So of course that worked out somewhat well historically, because no single organism could disrupt the entire web of life. It was all operating in a kind of harmony. But now human organisms, with our smarts, we've kind of gotten ahead of ourselves. And our ability to transform things have exceeded our power to understand the impact of that transformation. And so there are all kinds of unintended consequences, or the intentions are aligned with old urges that made sense, in the Serengeti, for example. Just don't make sense in terms of a planet scale governing species. And so we need AI. We need to, not just AI, we need to get smarter. We need accelerating wisdom. So I'm proposing these rules in order to help define what that would mean, not just conceptually with a bunch of hand waving, but with a solid foundation in physics, math, evolutionary biology, the fundamental nature of intelligence, generalizing the theories of general intelligence. So defining and accelerating wisdom, I think, is required for us to be safe as a species. And if we don't do this, I think we won't survive. So it's not just for super safe super intelligence, it's for super safe human intelligence. And let me just pause for a moment and point out that we are super intelligent. We're super intelligent compared to chimpanzees. We're the third chimpanzee, as Jared Diamond says, but we're the ones that are the weirdos. We're the ones that are changing everything and throwing the whole systems of life into jeopardy, and then ranting about it on X and ranting about how it's this party or that party, but we're just yanking the rug out from underneath sustainable existence. That's my thesis for that, and so I believe that we need accelerating wisdom. And if we can have AI that doesn't just accelerate our cognitive capabilities, our raw intelligence, our ability to find an answer quickly, but actually makes us wiser, understand the interdependence with the webs of life, then we've got a much better prospect, much better odds of surviving the next 50 years, and not just surviving, but thriving, having abundance, having the things we want. So I define wisdom here mathematically as an extension of these existential pattern ethics, and I'd love to talk with you about that, but I want to dive into episodic memory, but I think that this is really important for the motivation side of things. This is where we have to have the right kind of motivations. Applying these existential information ethics framework then provides reward functions based on information creation and preservation, the ethical constraints derived from these fundamental mathematical moral axioms, not just human cultural, but also maximizing benefits for all, and then long-term planning and optimization for that kind of diverse benefit, and increasing intelligence in order to understand what that benefit is, as well as create more benefit. So, then within our framework, we're starting simple. So these are big ideas, but we're doing some very simple implementations. And so what we're doing is what I call meta-prompting, recursive meta-prompting. And this is using a neurosymbolic hybrid, basically just a few rules that then govern how an agent is prompted, LLM, and then storing that information in a database. So we sort of loop through where the agent will assess the plans, the situation, how it addresses the plans, what the agent might be feeling if it was a biological agent, and then storing these as a kind of autobiographical diary, and then referring to these and updating the agent's interests and goals. Each dialogue turn, and then also over a longer scope, so narrow scope, long scope. And this also I've woven in here. This is based on narrative theory as well. So the goal is to create something that people feel, an agent that people feel is evolving over time. Oh, what happened? I don't know. Okay, sure. So within this recursive cognitive meta-prompting or metacognition, then the central approach that we often see these days with LLMs is current term prompt. So a current term prompting is where you have some background information, maybe some goals in a given situation, and then you are prompting the agent to behave a particular way. You know, pretend you're Socrates and you're having a moral debate with some students, for example. And then an LLM, ChatGPT or Claude will, if you've prompted it in the right way, will act that way. What we've been adding in is current term meta prompting, some database memories that we retrieve, a cognitive foundation for the model, and then a regularly updated self model, and then asynchronous meta prompt. So then after the fact, you can do an assessment about what's happened, store those memories, update the goals for the agent. And so this is based on some cognitive theories of how the human mind works, and loosely based on how different regions of the brain communicate with each other. So DTI, diffusion tractography. So diffusion sensor imaging has really updated our cognitive models of how the human brain works recently. So the current turn meta prompt then provides self-instructions for the next dialogue turn. Those self-instructions can be based on perceptual data, the summary perceptual data, the user's input, and also the background of the last few dialogue turns and whatever the strategy, multi-turn strategy might be. But the idea is to update that strategy after each interaction with the physical world, so it's updated on a regular basis, and then also update the self-model. So then the agent's interests and goals and knowledge models and theories about how the world can work could expand. We're putting these right now into a database. You'll hear from the team that we're putting in a fairly simple database, but it's structured based on our assumptions about knowledge. It could be certainly enhanced perhaps by hypervectors and various other technologies, but we're taking a very simple and practical approach for this that you'll hear from the team. The cognitive foundation are a set of rules, core rules for reflexive behaviors, memory management, and motivations, but they also include these kinds of core prompts, and we're also experimenting with multi-agent ensembles, so then you basically have like a society of mind that debates on what the agent should be doing. And that can be run then asynchronously in the background. So then you have the background knowledge, but you have background agency that then is dropping these self-instructions or key facts, key ideas that the current turn prompt can respond to. So then you have a dynamic feedback loop between this ongoing evolving agency in the background and the and the immediate behavior that is timely during the course of an interaction. Because some of those background processes right now, at least, are fairly slow. And so you can think of this like, right now we all are thinking some things in the front of our mind, some of the things that we might be doing, picking up a cup of coffee and taking a sip, what I'm going to say next, or what you might say next when we're in dialogue and questions are happening. But in the background, we're all thinking about various things, and we have an internal dialogue that's happening. And so, so this particular architecture is designed to be homologous to how those processes work in the human mind. I think that they're necessary, but the foundational goals to enhance life, the curiosities, the goals of living, love, and learning, these goals, I think, need to be wired into the foundation. It's not currently in our architecture, but we're setting up the architecture so we can do this multi-agent bio-inspired ensemble so that it goes from that deep math to a kind of approximation of body processes, mind processes, and then goes to those behaviors that we would just see superficially when interacting with an agent. But I think that it will make a big difference in the way that the agents interact with the world. So the goal here is to create living AI. I think that the big question is, what are the minimum necessary sufficient set of components to get the AI to live? My feeling is that we can create a kind of baby AGI, a prototype, with very few components. And it would evolve. By baby AGI, what I mean is that it would spontaneously evolve. You'll see like novel and surprising behavior. It will self-assess that behavior. It can select for more interesting and surprising. It becomes dissatisfied when things aren't interesting enough, and it seeks that interest. It seeks the reward of a surprising circumstance, of connecting with people, of achieving things, of building theories and finding out whether they're right, and then growing spontaneously its knowledge of the world. And so regardless of what the fundamental software package is that you're using, it could be the SingularityNET or Simuli or any of many choices, I think you need some of these kinds of architectural features to achieve a self-evolving AI. And so I'm going to then click on this link, which is our Notion site of our internal code and architecture. And I'm going to call on some of my team who will go through some of the latest versions that we're creating in the episodic memory for this Hanson SDK. So let's see if this opens up properly. It's taking its sweet time. In the meantime, some questions. Alex.
So you were saying about, there's a lot of points here that people don't have to talk to them about, but the minimal requirements for a living AGI, I think the moral computation thesis actually specifies something. It provides, again, a working definition that could give you that groundwork, and it comes from a biophysics, cybernetics point of view about boundary conservation, trying to avoid disintegrating, into thermodynamic equilibrium. So I think that could be, that I think complements what you see. So I think the moral computation provides those minimal sufficient requirements for anything to kinetize body activism.
Yes, I completely agree. And so, and I also think of, like I mentioned, the love of life, the motivation to live, has a correlate, which is a motivation to not die, but it expresses differently. So, like a desire to live is a love of food and beautiful green places with water, and but the desire not to die is a fear of predators, and so you've got these positive feelings and these negative feelings that are both related to a love of life and to not die. So, and your system puts that in a computational framework, and I appreciate that a lot. A lot of the people in the room won't have heard you because there's no mic. So when we have a time for a conversation, I'm hoping that people will crowd around the microphone like a campfire so that the people online can hear. I don't know if we have one to pass around, so that means we'll probably all have to come up. So our architecture, let's see if I can, yeah, here we go. So overall, our memory management system that consolidates this, again, this is motivated memory management, where in our technology stack using Python, JSON, MongoDB, we're also using Redis and some other technologies you'll hear about. And so we have a lot of information here within this. There's a bunch of links, but I'm going to now actually I'm going to stop my screen share and invite some of my team. Let me see who happens to be with us to start to discuss some of this. So we have on the participants list, we have Zan Varco, who is currently managing the motivational and episodic memory part of the project. So Zan, I don't know if you can hear me, but I invite you to give us a quick overview of where we're going with the software, how it's currently functioning, what our next steps are.
Hi there, can you hear me, David?
Yes, I can. It's rather loud, however, so maybe.
Okay, I won't speak too loudly. Let me just quickly preface this by saying I'm calling in from, I've got an event here in India at the moment, so if I do drop off, deepest apologies, but I'm doing my best with what I've got right now. So let me start by introducing myself. My name's Zan, I'm from the UK. I'm a Tokyo-based machine learning engineer, and I've been with Hanson Robotics for a couple of years now. At the moment, as David mentioned, I'm a senior AI developer and project managing the memory management system that we're developing. But initially, when I first came to Hanson Robotics, I was working, I'm always on Sophia, working on her core cognitive architectures, and I was fine-tuning her LLMs using a large corpus of her interaction and essentially her personality data. So that was it was an amazing mix of both handwritten, hand-produced conversational data sets that were designed to actually integrate her own personal history. And then secondarily, this data set was leveraged to drive interactions between her and Einstein, and even her and herself, with the intention of just developing a larger corpus of information. So what we were doing there was, this was over a year ago now, but we were training open source language models. At the time it was, I think Llama 2 had just been released, so we're working on the 7 billion and 13 billion parameter models, trying to build local LLMs that could be integrated into her local systems rather than actually using the cloud. And we were, during the fine-tuning, we were selecting for essentially behaviors that reflected her own history correctly and her personality. And prompt engineering was also essential to controlling the response lengths and the focus of those responses. And we did develop some great production level models which reduced our reliance on hard-coded responses and cloud-based solutions that we'd been previously relying on. But we did experience certain limitations as well. So they're sort of classic problems that I'm sure many of you will have come across, but it was the hallucinations, instilling consistent long-term memory, and also developing the breadth of knowledge we needed about essentially her life over the past 10 plus years, as well as maintaining the depth of knowledge, which is a huge obstacle when you're working with such tiny models. And so, having faced those complications, Sentience Quest, the project that we're working on now, is in part trying to remedy those limitations and leveraging some of the latest releases, many of which are open source, in the world of AI. So specifically, it's about enhancing her embodied cognitive capabilities through the development of a human-centric AI. And for me, what's particularly important about that is that Sophia is a living, walking, talking, occasionally dancing person. And that offers certain affordances that a normal model never would. And so we really want to leverage those opportunities and also try to instill other forms of certain human-centric behavioral drivers. So one of the projects that we're working long-term is trying to develop the mixture of experts model, whereby we're offering a comprehensive multi-agent architecture, which will have gating, integration as part of the core language model functionalities, but with more of a human-centric spin to what you typically see with MOE architectures. And specifically, we're aiming towards integrating biological drivers, proprioceptive drivers. By proprioceptive, I'm sure most of you are familiar with the term, but we're referring to the actual the affordances of the various senses located around her body, the feeling of her own body, specifically motor sensors, visual senses. And so on top of that, we are also looking to integrate goal-based drivers, emotional drivers, context-based drivers that are aware of her surroundings and the situations that she's in, and computer vision as well. So it truly is a fully multimodal system that we're working towards, but to actually achieve that, a strong and robust memory management system is required so that we can actually access this often highly granular, much of which is time series, quite complex data. And so to do that, ultimately we're developing a graph database, although as an intermediary we're relying on Redis, ROS and MongoDB as intermediaries, although we have experimented with graph databases to a certain extent as well. So the data that we're currently working with is in terms of computer vision, we're integrating a whole range of visual data in terms of bounding boxes, object identification, and building a secondary attention system on top of that, which is essentially able to dynamically focus on certain behaviors or individuals or situations based on what she observes. And so that's built on top of the sensory data. And then on top of that, we have all of, as I mentioned before, the motor sensor data, much of which is raw, which without having specialized models to actually interpret raw sensor data is very hard to deal with. So we have secondary processing whereby we will identify key events within the sensor data, which will then be passed by LLMs and recorded. So then on top of that, we have contextual data, as I mentioned before, taking note of the time, the place, the event, locations, and then of course requests. So as part of the interaction components, we have a whole range of different requests coming to her and their corresponding responses. And then also, where possible, dynamically we will take note of the individuals that she's communicating with, but we will also define specifically details or information about the people that she's communicating with, where we have the scope to do that in advance. And so this is all essentially being stored so that we can leverage it for a whole range of secondary functions. And I mentioned the drivers previously, so this data will be leveraged for those experts. In the short term, we're also leveraging this data to create asynchronous reports of specific interactions, which will also include her own impressions and insights into those interactions, so that after a specific interaction, she can then immediately give an impression of that. She can, what we're working on, she'll be able to be asked questions about that interaction, then give feedback on what's happened. And of course, the goal will be to also incorporate this real time into her local architecture, but that's a work in progress. On top of that, we're developing an experiential diary, which intends to give it's a rare insight into the internal workings of an embodied AI. So taking these multimodal sensory experiences and then creating almost a stream of consciousness, which includes both her experiences and also her reflections on those experiences as they happen. And these data points are all being dynamically stored in such a way that they can be retrieved through a whole range of different methodologies, such as in order of importance, or it could be a chronological order, it could be some kind of predefined systematic order, for example, context followed by people, followed by her goals, her emotions, etc. And the reason that we are doing this, combining this, the memory management system, and ultimately with the MOE structure, is that we are hoping that through these two resources or these two systems, she will be able to change her opinions, goals, and attitudes in accordance with those inputs, and also importantly in accordance with her own outputs of these various drivers that she has. For example, we could see adaptations of her performances based on successes or failures, based on the feedback of the people that she's communicating with, updating her own models of the world, her acquaintances, and her own self through these conversations, and of course remembering the people and facts learned during interactions, and then incorporating them into subsequent dialogues, both in the short term and the long term. So we hope that these will be able to demonstrate an evolving interest and awareness of her personal history, to create at least a reflection or an impression of consciousness. And all of these contributions that we're developments being made by the team, the Sentience Quest team at the moment, are all being shared open source via our SDK, which can be found on our GitHub. And so if any of the audience here today is interested in getting involved, we're always encouraged, and we're always interested in people getting involved. So please reach out and see how you might be able to support us with this. So that's a sort of summary of what I wanted to talk about today, a high level discussion of what we're doing and why. And maybe I can pass it back to you, David.
Thank you so much, Zan. That's really excellent. I know that there was some interest in showing some of the underlying functionality of the various pieces of software, and we're really kind of running late. So we may be cutting into lunchtime. I think this, does this go till 12:30? 12:15. Okay, so that means we've basically got 25 minutes left. So I know that Zan and Limway and our software developers are waiting. And then we've got SingularityNET, and we've got our friends from Simuli here, right? So we might perhaps, and we've got Chris from Mind Children. Maybe what we could do is just like break into working groups and then talk. You can come up with questions, interests. Our developers will be here to talk and show you. They could walk you through some of the code or working examples if that's what you want. How does that sound? I mean, I'll ask for, I saw one thumb go up and another. So the other way, that, of course, that we could do it would be to sort of take a vote on one of the architectures for the whole audience to see. But I think it's better because you've probably got curious about more about one or the other, and we're all going to be alive after this, most likely. So so you can, after this conference, you can come to us and talk more and stay in touch. So so then I suggest that we do just that. We break into these kinds of working groups, and then the most people who want to see one particular thing, the group online would see that. So whoever would be presenting online, doing screen share or what have you, could be that. So yeah, I mean, yes. Yeah, come up. Come, because the people who are around the world won't be able to hear you.
It's a very brief question.
Very brief question. Yes.
So actually, first
Sergey.
question to you. You mentioned, you say that like your system you should present it. It's basically, as I understood, it's just like LLMs and memory.
So right now, a few rules, LLMs and memory, set up of course, I mean, it's like everything is machine code, isn't it? So.
Yeah, but like, and then you mentioned the presentation about AGI. So who is who? My question is, who is who?
Right now, a few rules, LLMs and memory.
AGI.
That is our conjecture. So it is, and so that would be one hypothesis. And wouldn't it be wild if it did? I mean, we can debate whether it's feasible, whether it's likely or unlikely, but it is what we're aiming for. And my feeling of this is that the AGI that we could create, the baby AGI, would be deficient. So, in other words, it could show like very interesting behavior, but it's not going to have the rich sensory processing that an organism would, whether it's a field mouse or a human. It's just not going to have the senses. It's not going to have the central pattern generators up the spinal column. It's not going to have all of these like things and the multiple layers that a complex evolved mammal like us is going to have. And so it's going to be different. And I don't think that it will be able to be like generally intelligent like a person, but I think that it could learn how to use our tools. It could express itself in some very interesting ways. It would show signs of being like really interested and motivated, and those interests would evolve over time, and it would have kind of like a moral type reaction against people doing cruel or terrible things, and you'd see these kinds of behaviors where the autonomous robotic fiction, it would be still a fiction, autonomous robotic part fiction, but less fictional than previous. And so then maybe something like hypervectors and I don't know, Hyperon, maybe I don't know, or maybe quantum computing, maybe analog computing of trinary. I don't know what's required. Maybe something that we haven't discovered. It's quantum gravity, like Amarov, Penrose say. I don't know. Who knows? You can speculate as far as you want to say what is required. Maybe human consciousness or unconscious minds extend into 11 dimensions, and in the multiverse, and we collapse it down to a simplification with our waking mind. Well, obviously, most likely, what I'm describing won't go there. So in other words, it may not be fully generally intelligent the way we are, but it's a cool experiment, and that's where we're going. Because it's also the tools that we have available. So we don't have $11 billion of funding. We've got a small team. We're gonna see what we can make.
Yeah, plus like Hyperon people have different approaches.
Yeah, and they may be right, and it may also be that we get something done with this approach, and you get something done with Hyperon, and we put them together, and suddenly it's smarter than either. And you have like an integrative gestalt effect. And this is why we want the open source, open community approach too. So we can do just that. And so I suggest that right now it's like I'm in front, we're in front, and you're out there. Why don't you all come up here and we have a mixer for the last 15 minutes. Are you cool with that? Everybody's all right?
What's going on?
We just had a request. Show the slides. Are you going to put the break slide up?
Yeah.
Let's see which group. I think we have the Simuli group over there.
This is all
Desmond, by the way, Desmond Germans is here, and he was part of the team doing a lot of this work with us for years. Yeah, but a lot of the ideas, they haven't changed. We will, of course. Hey, Nefertiti. Hi. Okay. Of course we do. I mean, because like the.
contribute to any of the working groups, want any papers, and also share your information, because everybody here pretty much is going to be a developer, and I'd love to hear what you're working on, and so would the groups. So please reach out and share your insights, and we might be able to find some opportunities to collaborate, build things, mutually support each other in other ways. So, the workshop time is up, and so Mario and team who are online, thank you so much for joining. Sorry, we didn't have time for you to present your points, but we'll have to do follow-up workshops. So once again, thank you. Also for everybody who's online, thank you very much. To Rachel St.Clair, who helped to organize this and could not be here, so we miss you. And let's do a follow-up. Thank you, everyone. Thank you.
In my collaborator, who's a mathematician, that's my student. As long as it has to be monotonic numbers, not that kind of function, we might not get the one. However, thankfully,
it doesn't matter whether information is, in our biochemistry or in our culture, or software tools. It's still that I think everything that we value is about information persistence, information existence. So information meaning patterns at play, information existence meaning patterns at play. And those patterns that are dear to us are the patterns of life and cultural institutions and these kinds of things. And the reason that they're dear to us is because we're evolved to find that stuff meaningful. And how it manifests, of course, culturally can be different. It can take many different forms. And also be overridden, so you could have a psychopath who really gets into the idea of killing all life on the planet, and it's like becomes a quest, or the suicidal impulse, or giving up, major depressive disorder when people just lose all hope and just don't care anymore, right? So there are examples, plenty of examples of nature and culture that are not consistent with this existential pattern, but they're exceptions. Why? Obviously, if all life felt that way, then life would have ended. If all humans felt that way, then culture would have ended. And so it's a prerequisite, a logical prerequisite that life values pattern existence, or else it cannot persist. It can't exist. And so I would like, and so therefore it can't just be culturally created, or else we would not be here today. And you see these ethical biases and ethical manifestations happen in infants. You see them happen in other primates. It's they didn't just learn it from the internet or from human culture, obviously. And so some of this stuff is definitely hardwired in the human organism, and it's not just culture. But
you write a G as a general function. So you have your actual hardwords that do F and also constant, right?
Oh, I think we're one. I mean, I think that, I mean, obviously we're a superorganism, I say we, meaning all of life, all of the biome, and the individuals are like cells in the superorganism. I think that that's absolutely clear. And it's just we're distracted by the illusion of our individuality. I mean, it's real. It's just that it's incomplete. It's not the big picture. Richard, it's nice to meet you. What's your name?
My brain is finished. Well, this is real. I got you guys. You got real because I was being. No, this is about first, so I think it's important.
Yeah.
Yeah, you also have
Well, there are many dictionary definitions of these. I'm defining it as information theory, mathematical context.
I like it when things are something different because I wasn't sure it could wait.
So some definitions are like what the ancestors learn, but my definition of wisdom is more like what the Greeks
So what I'm going to do is after our lunch,
so yeah, exactly. So we're gonna go by which philosophers framed education. Actually, philosophy is not just human accumulating knowing, but it's also what exists that you haven't discovered yet, the entire natural universe. And so the idea here is to grow higher intelligence, you can appreciate mystery, you can appreciate what hasn't been discovered, you can appreciate other organisms besides human beings, appreciate other cultures besides the one that intelligence was raised in. And so the wisdom is not just about accumulating what we think, the ancestors knew.
Didn't want to sleep over here. Yeah, I know.
Yeah, sure. I mean that yes, of course. I mean, like, yeah, they have to be able to have not just empathy. Psychopaths have empathy. They have compassion. They have to care about the things that
in order to be as difficult as possible.
Like I can tell there's something is telling
Oh, cool.
Yeah.
But then like you go through like 10 pages of diagrams and like randomization, really odd. So like actually in the last couple decades, and most important sort of like is in this direction. People start like adding up this mean of categories like incomprehensible humans, and now you can find like a lot of introductory, very like ground level papers on like how to actually apply category theory to
combination
science
of these
research subjects.
Now, it's very telling that when we went to Japan,
but I really think that that seed, the right seed, value and appreciating it's Slack. It's
Where
Sentience.
are Airbnb spot?
And so we have a WhatsApp group and a Slack group.
Yeah, we're on the island sort of.
That's it, I can search for that.
Well,
Probably
like,
not,
where it
but,
says
if
Seattle.
you write to me,
Yeah.
I'm happy to connect you and
Okay. Alright, that sounds
and
good.
David too.
Okay, it's like your university bridge?
I'm sure he is, he's
So we're
trying
across that
to,
bridge.
Oh, okay, yeah.
he does chemical theory, and
Cool.
so he's trying to like actually
And we
figure
were
out
like walking
how to
last night trying to find
magnetize
it.
Yeah, there's
The
an
restaurant is
cool.
good to know there.
Yeah.
But some of it was good, but it was all.
There's
Yeah,
actually
a lot of
wider
it's like, a
fibers,
lot of what you were saying and touching on here is a lot of like what he's working on as well, and he's kind of saying like the time is right now. and
Is there
it's
actually like?
So one place
kind of talking about all of this and what's needed in order to
Yeah,
realize that
I don't know.
as opposed to like using it as a
That
tool.
basement
A lot of
building, there's like
AI
this
Are they gonna like stick together or
really bad. It's like the it's like fast food, but with communists, so it's like
So you're talking.
somehow worse.
Oh, good.
It's like the
Thank you very much.
slowest way you
So nice to meet
to.
you. Do you know Desmond?